So good morning, everyone. Welcome all to this plenary session of the International Congress of Mathematicians. I am Luigi Ambrosio. I am a professor in mathematical analysis in the Scuola Normale. And for personal and scientific reasons, I am very happy to introduce Camillo DeLellis, now professor at the Institute for Advanced Studies in Princeton. Well, I think it's very difficult to summarize in a few words the spectacular career of Camillo, initiated here at the Scuola Normale and in Pisa University for 7 years, then for the first postdoc position at the Max Planck Institute in Leipzig, then a professor in Zurich for many years, and eventually at the Institute. Among the many honors received by Camillo, I would like to mention in particular the Fermat Prize in 2013 and the Cacciopoli Prize, a distinguished prize of the Italian Mathematical Union in 2014. Camillo is a leading figure in two main areas of mathematical analysis: partial differential equations and in particular fluid mechanics. His groundbreaking works on exotic solutions to the Euler equation and to the Navier-Stokes equation, and also geometric measure theories, a fundamental series of papers with a large group of collaborators on the regularity of minimal surfaces. These topics are really at the technical level also quite closely related, as the experts know. And today, Camillo will focus on the second one. So I'm happy to give the floor to him. He will talk about regularity and of regular and singular minima surfaces. Thank you, Camillo.
Thank you very much. It's a great honor to speak at this International Congress of Mathematicians, and I wish to thank the organizing committee for inviting me, and also the Liceo Giacomo Leopardi at the beautiful town of Recanati, who's hosting me and a bunch of friends who are following this event live. So let me dive immediately into the topic and start with one of the main protagonists of this talk, which is the so-called plateau problem, which can be stated in the following way. So given a one-dimensional contour gamma in the three-dimensional space, you're looking for the surface or the surfaces sigma of least area which spans this contour. This is a problem which is named after the Belgian physicist Joseph Plateau, who proposed it to model the shapes of soap films in the 19th century. So what this means is that if you take a wire and you dip it in a bucket of soap water and pull it out, you are actually expecting that the soap film, which is formed, is a surface of least area, which is of course attached to the wire. Even though it's called the plateau problem, actually in mathematics, minimal surfaces appear as early as the 1760s. In the work of Joseph-Louis Lagrange, which was actually written in Torino while he was still there. And in this work, Lagrange gives the foundation, the start of what is called nowadays the calculus of variations. And he's mostly concerned with one-dimensional problems. In fact, for most of the paper, he rederives solutions of famous problems like the Brachistochrone and also for new ones. But in the appendix, he actually considers the area of two-dimensional graphs. And this is actually a copy of the appendix, and you can see that it's literally considering the area of a graph, which is written over here. So this is the graph of a function which is represented by the Greek letter z, which is a function of the two independent variables x and y. And you see that he has the square root of this quantity, and p and q are just the partial derivatives of your function in direction x and y. Okay, so in a couple of pages, after introducing the area functional, Lagrange derives the Euler-Lagrange equation for extrema, and he actually does that in a surprisingly modern way. So you see here, he's actually saying that a necessary condition is that these two differential forms, which I have written over here, are exact forms. And in fact, if you at this point write down the conditions for these forms to be exact, you actually find the classical equation for the minima surfaces in 2 dimensions. And I'm not completely sure whether these claims are correct, but I'm hoping that some historians will check and correct me if I'm wrong. But it seems this as the first time that there is a multidimensional Euler-Lagrange condition which is derived, and also the first elliptic partial differential equation which is ever written in the mathematical literature. Okay, so let me now reformulate it in a way which is more modern and which is heavily studied in modern mathematics. So given an m-1 dimensional surface, which we will denote by gamma, which is maybe going to be in a Euclidean space, but more generally could be in an ambient Riemannian manifold, we are looking for the m-dimensional surface which spans gamma and has least volume. Now, as soon as you formulate this question, one very natural thing that you could ask is, what should we actually understand with the words surface, spans, and volume? And this has been a subject of heavy investigation in the last century. And one first possible answer, which was given by Douglas and Rado in the 30s, would be to actually fix an abstract manifold sigma prime and look at maps phi, which are going from sigma prime into M, with the property that when you restrict the map phi to the boundary of this model surface, you actually have an homeomorphism onto the fixed contour gamma. Okay, so this is actually a fruitful approach, especially in 2-dimension, but it has some drawbacks. So first of all, it's very difficult to generalize it in higher dimension. But secondly, you see that you're also kind of imposing some topological restrictions on your surface. So for instance, if sigma prime is a disk, your image is going to be, for instance, if phi is a diffeomorphism, it's going to be like a disk. It's not going to create some more complicated shapes. Okay. So in geometric measure theory, which is one heavily studied subject in mathematical analysis, there are several proposals for what you should understand as surface, spans, and volume. And these proposals give several different approaches to the existence question for the plateaus problem. We could group them into two big philosophical trends. One of them, I will call it set theoretic. And one pioneer of this approach is Reifenberg in the 1960s. So loosely speaking, you're actually looking at a surface which you just assume is going to be a closed subset of your ambient space. To identify a volume for this surface, you actually fix a measure, and the popular choice is the Hausdorff m-dimensional measure. And when it comes to understanding whether sigma spans gamma, you're actually imposing that gamma is trivial in sigma in some topological sense. For instance, in the case of Reifenberg, he uses the Chesh homology. Now, that's one possible approach. Another possible approach is what I would call a functional analytic type. And this, we're going to take as an example the pioneering works of De Giorgi in the 50s. So in this case, what we're going to do is we're going just to fix a class of desired surfaces sigma, which are the ones we like, for which we assume that we know what the boundary and what the volume is. So in the specific examples of De Giorgi's work, these are actually boundaries of smooth open subsets of the Euclidean space. Okay, at this point, we want to decide the topology on this space, which typically is not going to turn out to be like complete or compact. So then we want to complete this topology. And we get a space of generalized surfaces on which we hope to extend the notion of boundary that we have on the nice surface and the notion of volume via some continuity. So, so you see over here that I said that we actually want to decide a good topology. And good means that we hope that for the topology that we have chosen and for the completed space, we actually can apply the direct methods of the calculus of variations to find minimizers. Okay, so let me give you a very simple example of set theoretic approach. I mean, there are many. And I'm going to restrict to the 3-dimensional space. So you fix a closed curve gamma in R3, and you take your sigma closed set. So we know what is going to be the volume. It's going to be the 2-dimensional Hausdorff measure. But what do we mean by the fact that sigma spans gamma? So here's a proposal by Harrison in 2011. So you're going to say that sigma spans gamma if sigma intersects every smooth closed curve eta whose linking number with gamma is 1. So you're imagining that you have this contour gamma. You take a small loop eta, or maybe a larger loop, which links to gamma. And at that point, you're imposing that the surface eats this eta somewhere. So the surface somehow is not leaving any hole, sort of. Okay. So now let me give you an example of functional analytic approach, which will play a big role in the rest of the talk. So you start with your desired family of surfaces. So for us, this is going to be the singular chains with coefficients in some normed group. So to fix ideas, and this is in fact the most relevant case I will examine, you think that your group G is actually the integers. Okay, so what do we mean by singular chains? So we take formal linear combinations of smooth images of m-dimensional simplices, they are these sigma i's, and we weight them with elements in our group. So in particular, in this case, we can take ki's, the coefficients, to be integers. Okay, at this point, we have a very well-defined notion of boundary, which comes from topology, and we also know what is actually the volume of the smooth image of the simplex we can compute through formulas, and then we're just going to weight this volume by, say, the modulus of your coefficient ki. That's why I'm actually insisting that this is a normed group. Okay, so now I have to tell you what is the topology. This is a little bit more difficult, but if you keep in mind that we are interested in solving the plateau problem, in which the boundary of your surface is somewhat fixed, we can actually restrict our attention to a meaningful case, which is the case in which sigma 1 and sigma 2 have equal boundary. I have to tell you what is the distance between these two. And if you are in the Euclidean space and sigma 1 and sigma 2 have the same boundary, you know that the difference between the two of them is actually the boundary of a surface of one dimension higher. And you can take as the distance the infimum of the m+1 dimensional volume of this filling lambda among all possible fillings. So that's a possibility. Okay, so if you take this approach, you can actually build a theory in which you solve what I will call the oriented plateau problem. So Federer and Fleming in 1960 studied the completion of this space with the given topology, and they introduced the space of flat chains. But for us, for the case of the plateau problem, what is most interesting is actually the subspace, which is the space of integral currents. And the reason why we are in a nice subspace is because we are assuming that our boundary is fixed. So what is an integral current? So first of all, let me tell you what is an integral rectifiable current. So now, instead of having a finite sum, like in the case of integral chains, you have a series. Now, the coefficients ki are still positive integers, but the main objects are compact subsets of C1 m-dimensional oriented submanifolds. So they're not anymore images of simplices, but they're just going to be some pieces, but of nice m-dimensional submanifolds. And I'm assuming for technical reasons that these pieces are pairwise disjoint. Now, there's still one condition that I'm going to give you, and the condition is that when I sum the modulus of ki, so here I actually forgot the modulus because ki might have a sign since it is an integer. Well, okay, actually in the slide, I'm actually assuming, just without loss of generality, that it is positive because I might change the orientation if the integer is negative. I actually like that the series of the volumes of the pieces counted with their own multiplicities is finite. Okay, so now when actually do I say that T is an integral current? So I'm going to say that T is an integral current if both your current and the boundary are integral rectifiable. And somehow, when I'm interested in the plateau problem and I have fixed the boundary to be a nice surface, of course, the integral rectifiability of the boundary is an assumption which I have for free. Okay, so Federer and Fleming in their foundational paper in 1960 actually proved that the direct methods of the calculus of variation apply in this situation. So, and it's possible to take other groups. And in fact, one choice which will be relevant for this talk is the case of integers mod P. Okay, so now let me give you a little digression on rectifiability, because there's this concept which will actually happen many times in this talk. So take a set E. Now I'm going to say that this set E is M rectifiable if I can chop it into countably many closed pieces, Ki, which are in m-dimensional submanifolds gamma I, and some residual set, K0, which I'm going to assume has 0 m-dimensional Hausdorff measure. In a sense, I will neglect this set of measure 0 for the dimension that I'm interested in. Okay, so m-dimensional, so m-rectifiable sets are some sort of measure theoretic substitutes of C1 m-dimensional submanifolds, and they are ubiquitous in geometric measure theory. And if you compare it to integer rectifiable currents, you're just seeing that the difference between the two objects is that when I have an integer rectifiable current, I have some more data. I know the multiplicity of the pieces, and I also have an orientation for them. And moreover, I was assuming this finite m-dimensional measures, so this convergence of this series that we saw before. Okay, now, different approaches to the plateaus problem, so we've seen two, have actually different advantages. It's hard to say which one is the best, I think. It a little bit depends on what is your goal. So if you're interested in modeling soap films, for instance, I would say that set theoretic approaches are in fact better. And there are very recent papers that take a physical modeling of soap films and eventual a justification of why certain type of set theoretic approaches are better. But if you're interested in understanding, for instance, the structure of manifolds, if you're interested in understanding the homology, then the functional analytic methods are actually better suited for that. Now, even though there are several approaches, there's one gadget which is beautiful and very useful, which is called integral varifold. I'm not going to give you the formal definition of it. I'm just going to tell you that they look like rectifiable measures in the Grassmannian of unoriented m-dimensional planes. They were introduced by Almgren, and what is actually useful for us of this concept is that, in a sense, first of all, they are a very powerful generalization of the notion of surface for which you can make smooth deformations. And you can therefore define stationarity, so vanishing first variation of the area functional through one parameter families of deformations, and stability, so stationarity and non-negative second variation. But what is beautiful of this theory of integral varifolds is that pretty much any minimizers in geometric measure theory, in the many approaches that you can take for the plateau problem, actually give you stable varifolds. So it's a sort of umbrella concept for which, if you prove a general theorem, you're going to cover many applications. Okay, so now let me tell you, though, that you might be wondering whether we need these geometric measure theoretic notions of general surfaces. Maybe I'm just looking at minimizer for some given gamma, and maybe there are always smooth minimizers, and I actually don't need to consider generalized surfaces. Well, there are two very famous results in the literature. The first one is a theorem by Bobieri, De Giorgi, and Giusti in 1969. And it tells you that the cone, the 7-dimensional cone on the product of two 3-dimensional sphere in the 8-dimensional space, which obviously has a singularity at the origin, is actually an absolute minimizer for the oriented plateau problem. So what this means is that if I chop this cone with a 7-dimensional sphere and I look at any smooth surface, oriented surface, which has the same boundary, the area is strictly bigger. The volume is strictly bigger than the volume of this guy. And there is something similar that happens even in higher codimension, but it happens much earlier. So this is a theorem by Federer in 1965, which is based on computations of Wirtinger. So this is just a very particular case. So when you take this very particular complex curve, so 2-dimensional real surface in R4, if you identify C2 with R4, you will notice that you have a branch singularity at the origin. But very much like before, this is an absolute minimizer. So if I chop this surface with some sphere and I look for a competitor which is smooth, I'm actually going to get higher 2-dimensional volume. Okay, so in these cases, you cannot actually hope for having a minimizer which is fully smooth, an oriented minimizer for which it is fully smooth. So the regularity theory of minima surfaces in geometric measure theory is essentially concerned with three big questions. So when can we actually rule out singularities for your concept of generalized minimizer? How large can the singular set be in the worst possible cases? And if it exists, if there are singularities, what type of structures could they have? And of course, you can ask this question for all sorts of concepts. I mean, for stationary varifolds, for stable objects, for certain type of minimizers, for minimizers and certain other type. And so you have an array of different questions and settings. So the plan for the rest of the talk is to give you a tour on what is known about the regularity for minima surfaces in the literature of geometric measure theory. I'm just going to give you a little plan of the talk. So first of all, I will address the most general situation, which is that of stationary varifolds. And I will tell you what is Allard's regularity theory. Then I will tell you like what is perhaps the most beautiful result in the regularity theory for set theoretic type solutions, which is the theorem by Taylor. Then most of the talk will actually focus on minimizers which are oriented, so these currents that we have introduced. And we will address the case of boundary and interior regularity when we are looking at hypercurrents or currents of codimension 1. Then we will address what happens when you, instead of minimizer, you have stable surfaces. And eventually, I will also consider the case of the integers mod P as a coefficient group. I will then jump to higher codimension, and I will explain you the big regularity theory by Algren in the case of integer coefficients and possible generalization of that to coefficients mod P. And then I will actually address the boundary regularity, which is a much wider area, a widely open area in which we have many challenges and conjectures. And eventually, I will actually try to go to questions which are beyond the size of the singular set. I mean, whether it has structure, and then I will touch upon one of the biggest open problems, which is the uniqueness of tangent cones. Okay, so let me start with Allard's regularity theory. So there is this beautiful theorem by Allard in 1972, which is valid for every stationary varifold, which, if you remember my slide a few slides ago, is an umbrella concept which is including any type of minimizer for the plateau problem. And this theorem actually tells you that if you are at a certain scale, close enough to a disk of the same dimension for the varifold, and this disk is counted with multiplicity 1 when you have multiplicities, for instance, in the case of functional analytic approaches, then actually when you're sufficiently close, in a little smaller scale, so say in half the scale, you're a smooth perturbation of the disk. So you're fully regular. Now, why is this theorem very powerful? Well, it is very powerful and useful because even though I didn't tell you, the closeness in the assumption is meant in a very weak sense. And so it's widely applicable because this closeness will be true at several scales just out of measure theoretic abstract nonsense. Now, this was actually predated by epsilon regularity theorems of De Giorgi in 1961 and Reifenberg in 1964 in their own approaches to the plateau problem for their specific variational theories for the plateau problem. Now, in 1975, Allard actually proved a boundary version of this. So this time, instead of having a point Q, which is sitting away from the boundary, for instance, if you're solving the plateau problem, you have a point Q, which is sitting on the boundary. Of course, at this point, you're never going to be close to a full disk in no matter how small the ball that you take around that point. But if you're hoping for regularity, a reasonable assumption is that at a certain point when you're sufficiently, when you are on a sufficiently small ball, you're actually close enough to half a disk. And again, the assumption is that you're close to this half disk with multiplicity 1. Then again, the conclusion is that when you go at a slightly smaller scale, you're actually a smooth perturbation of it. Okay. So the epsilon in the epsilon regularity theory is because it's how much close you have to be. So this epsilon is going to be a small parameter to actually conclude that you are a smooth deformation of it. Okay. So now this has very powerful corollaries. So for instance, it tells you in the interior case that the interior singular set is meager. That is, the set of singularities is a nowhere dense closed subset of your stationary varifold. Now, it's an open problem since 50 years now, since 1972, to actually say even something slightly better about stationary varifolds than this conclusion. And we know actually in all the examples that we have at disposal that the singular set looks much smaller. Okay, even at the boundary, you have a powerful corollary of Allard's theorem, but this time it's not something which can be applied in full generality. So one powerful corollary is that if your contour gamma is sitting on the boundary of a convex set, of a convex open set, then the area minimizing integral current which spans gamma, so the solution of the oriented plateau problem, is fully regular in the neighborhood of that gamma. So what is important over here is that this convex set works as a barrier because of convexity and because gamma is lying on the boundary of this convex set. So your solution has to lie in the interior inside your open set U. And we will see that this is like a powerful starting point for your regularity. Okay, so now what is actually the key idea of all these theorems? So these are pretty complicated theorems, but pretty much the starting point of all sorts of similar theorems in the literature appeared for the first time in this paper by de Giorgi in 1961. And the idea is that the linearization of the minima surface equation is the Laplace equation. So it's very easy to explain this theorem for the graph of a scalar function. So the area of the graph is here the integral of the square root of 1 plus gradient u squared. If you make a Taylor expansion of this integrand, you find 1, which is a meaningless constant, and then you find the Dirichlet energy, and then you find higher order perturbations. And in higher codimensions, something similar happens. So you have a more complicated formula for the area of a graph of a vector valued map. But what happens is that the additional quantity which you see over here, for which you have the explicit formula, is actually of 4th order in the derivative of u. So it's just going to contribute to the 4th order piece in the Taylor expansion. Okay. So this means that minima surfaces, when the tangent of the surface is not oscillating too much, is very close to be harmonic. Okay, so now, as I promised you, in our tour, we actually turn our attention to set theoretic minimizers. And there is this beautiful theorem of Taylor, which is very, very powerful, which tells you that essentially for any sort of reasonable set theoretic theory in which you're minimizing among two-dimensional sets in R3, if you take an interior point, so if you're far away from the boundary, you are either smooth, or if you're singular, you're going to be diffeomorphic to some very specific behaviors. So either you're going to be diffeomorphic to the union of 3 planes, 3 half planes, meeting on a common line at 120 degrees, or you're going to be diffeomorphic to the cone over a tetrahedral structure, which, I mean, whose picture you see over here. Okay, so everything is fully classified. So you know what happens at regular points because you're going to be a smooth submanifold, but you also know exactly what happens at the singular set. There are generalization of this, very nice generalization by a few authors, but nothing which really is that definitive in higher dimension and codimension. The situation is even worse at the boundary. So now again, let me assume that you have a 2-dimensional set theoretic minimizer. Let me assume that you have a boundary point as a smooth curve. So again, you have Allard's theorem, which tells you that if you're sufficiently close to a half disk, then you are diffeomorphic to that model. So there's a work by David in 2014 that shows that if you are close to 2 half disks, then you are diffeomorphic to the model. And something similar happens if you're close to a triple junction. But unlike the case of Taylor's theorem, there is no complete boundary regularity theory. So one would like to have a complete list of models and know that if you are sufficiently close to these models, you're going actually to be diffeomorphic to it in a smaller scale. And that is completely lacking at the moment. Okay, so now let me actually migrate to the big bulk of the talk, which is going to be about functional analytic type approach, and in particular to the theory of currents. So there's a big difference when you're dealing with regularity theory for hypersurfaces or hypercurrents, if you want, and surfaces of higher codimension. So there is this beautiful theorem, which is the combined work of several further founders of the subject, starting from de Giorgi and getting until Federer in the 1970s, that tells you that if you have an m-dimensional integral currents with, so the functional analytic approach that we spoke about with integral coefficients, the set of interior singularities is actually rather small. It has codimension 7 in the current. And if you remember, this is optimal because we have this example by Bombieri, De Giorgi, and Giusti, which is a 7-dimensional area minimizing cone with a point singularity. Now, this can be refined, and you can say more. For instance, if you are in 7 dimension, you can say that the singularities are isolated. There's a beautiful fundamental work by Leon Simon in 1983, which tells you that you have a unique model for your singularity. And again, work by Simons and Neighbor and Valtorta, which actually tell you that this singular set is better than just having dimension m-7. They are actually m-7 dimensional, m-7 rectifiable, and they even have a finite m-7 dimensional volume. Now, if we go at the boundary regularity theory, this is also completely resolved by this fundamental work by Hard and Simon in 1980. And it actually tells you that you're always fully regular. You're never going to find a singularity at the boundary. You need to understand exactly what you mean by smoothness, though. So let me give you this example, right? So if you take two circles, right, and they are oriented in an opposite way, well, it's not too difficult to see that if you arrange the circles correctly, sufficiently close, the minimizer is going to be some lateral surface, which is actually a catenoidal surface. But if you orient the two circles in the same way, it's also easy to see that the area minimizer in the oriented plateau problem is going to be the union of two disks. Now, if I imagine to actually slide down the top circle towards the down circle and make them coplanar, you're going to converge either to a corona, so a disk minus the interior white disk, or you're going to converge in the second case to a disk and two copies of the inner disk, because the orientation of this disk and that disk is actually going to be the same. Now, for me, this is going to be a regular point nonetheless, even though it's not a point where your surface is a classical two-dimensional surface with boundary, right? So you are inside a single surface, and what is actually creating the boundary is that the multiplicity over here is 1, and the multiplicity in the central black dot is actually 2. Okay, so now this for me is going to be a regular point. And the theorem by Hard and Simon tells you that either you're a classical boundary or you're going to have actually a boundary formed in this way. Okay, in fact, there's a fundamental work by Shun, Simon, and Yao in 1975, which tells you that one of the key points of these minimizers is that they are actually stable. And in fact, they have a priori estimates on smooth stable hypersurfaces. This was turned into a regularity theory by Shun and Simon in 1981, which actually tells you that if you have a stable codimension 1 varifold, and you know that the singular set has dimension at most m-2, then actually the singularity drops all the way to dimension m-7. A deep theory was then developed by Vikramasekera in 2014 to actually reach the optimal assumption that if the singularity is m-1 dimensional, then it is m-7 dimensional. The reason why this assumption that it is an m-1 dimensional null set is optimal is because we already saw in Taylor's theorem that there are stable varifolds, solution of the plateau problem in the set theoretic sense, which form codimension 1 singularity. So for instance, these three half planes which are meeting at this line. Okay, up to date, it's a complete open problem whether you can have regularity for stable Eiber varifolds without any assumption on the singular set. And what you would imagine is that for stable Eiber varifolds, the singular set is going to have codimension 1 in your varifold. That's what you would sort of expect from the examples. At the boundary, there's even less which is known. So there is something which you can prove by using a very cute trick by White, which is very nice, and it gives you a priori estimates at the boundary if you assume it has multiplicity 1 and there is a convex barrier. And this is written down in this paper by myself and Filippo Pellandini in 2010. But as far as I know, nothing else is known. So now let me actually turn to different coefficients. So let me see what happens if you are in the coefficient group ZP. Okay, then an area minimizing m-dimensional hypercurrent mod P if P is equal to 2, the dimension is the same as the case of integer coefficients. In higher moduli, what is going to happen is that the singularity is a C1 m-1 dimensional submanifold. So it has dimension m-1, but it is regular, plus an exceptional set, which has even less dimension. So now this was proved for P equal to 3 by Taylor in 1973, and then was generalized to any P odd in this paper by myself, Hirsch, Marchese, Stewart, and Spadaro in 2021. And this was building on works by White and Simon. And there's a beautiful proof by Minter and Vikramasekera, which is actually using Vikramasekera's theory of stable varifolds, and which goes also beyond the statement. Now, for P even, for the special case of 4, this was proved by White in 1979. But the general case was actually addressed by myself and my collaborators in 2022. And this is building on a big number of previous works. And I will actually tell you more later about why this situation is much more difficult. Okay, so now let me jump from codimension 1 to higher codimension, which happens to be extremely challenging. So in the area, it's famous that there is this huge book typewritten by Halmgren in 1980 of 1,728 pages, which is proving that if you have an area minimizing m-dimensional integral current in higher codimensions, so this time this n actually is not bound to be 1, but it could be 2 and higher, then the singular set has dimension m-2 at most. And again, this is optimal, because if you remember the example by Federer, you had a 2-dimensional solution of the oriented plateau problem in R4 with a point singularity. Now you could ask, okay, so what is actually that makes Almgren's theorem so crazily difficult? So why is it actually that painful to prove this fact? Well, so we know an example, which is an area minimizer by Federer, and which has a branching singularity at the origin. What is actually bad about this example? So what is bad is that if you zoom in the singular point, and by zoom in, I understand that I take a ball of radius r and I make an homothetic rescaling, then the homothetically rescaled surface has this formula. And you see that in the equation, there is this little r here popping, which is actually a small number, right? So now what happens when you actually take r going to 0? Well, when you're taking r going to 0, this sigma r actually is converging towards a double copy of the disk z equals 0 in the complex plane. So now you take r smaller and smaller, you're closer and closer to this situation. That is, you're close to 2 copies of the disk, but you're never diffeomorphic to it. So you can't hope for having a Allard type regularity result. So 0 is, in other words, a flat singular point. And you can make much worse examples, because I can tweak this example a little bit, in which I replace z with z minus w to the power q. And you see that over here, I've put this w to the power 2q plus 1. And the idea is that I have a very smooth base. Instead of the disk, I have the graph of the function z equal w to the q. And the singularity is a tiny, tiny, tiny perturbation of this smooth approximation. And so it's kind of difficult, you can imagine, to capture the singular behavior, since you have to mod out a regular behavior, which is very, very close to it. Okay, so let me actually give you Almgren's theory in one slide, because it's going to be useful also for, like, the end of the talk. So Almgren essentially proves in his book the following fact. If you are area minimizing and you are looking at a singular point, so a point in which you're not diffeomorphic at any scale to a disk. Nonetheless, at any scale around 0, when T is sufficiently flat, you can actually construct 2 objects. An osculating smooth manifold. In your example, this was going to be sort of the best smooth approximation to your surface, in a sense. So the z equal w to the q part in the example. And then on top of this smooth approximation, you have something which captures the singularity. The something which captures the singularity is a q-sheeted harmonic approximation of your current on the normal bundle of your osculating manifold M. Okay, now the upshot of his theory is that the harmonic approximation is non-trivial, and you can kind of understand it much better because it's an harmonic function, even though it's multi-valued. And the fact that it's non-trivial, it actually obstructs the clustering of too many singular points at 0. So it kind of has a non-trivial behavior, which does not allow you to get a sequence of singularities converging to 0, kind of. Or, you know, it allows it actually because it allows something of dimension m-2, but somehow these singularities have to align in a certain particular way. Okay, so in a series of joint works by myself and Lellis-Spadaro in between 2009 and 2016, we actually found a more efficient way of dealing with the theory of Lagrange. So we used some other technology to treat multi-valued harmonic approximation, but we also gave a much shorter and more flexible construction of this osculating smooth manifold. And so you can go nowadays much beyond Lagrange's theory. So already in 1988, actually, Chang proved essentially the counterpart of Federer's theorem in higher codimensions. So the fact that if you are in the special situation of two-dimensional integral currents, not only the singular set has dimension 0, but it really consists of isolated points. However, he actually needed a suitable upgrade of the center manifold of Lagrange, which is the most difficult part of Lagrange's proof. And the rigorous existence of this object that Lagrange needed in 1988 is actually achieved in a work by Spadaro, Spolaore, and myself in 2018. Now, a very big open problem is whether you actually can go beyond just the dimension bound, even when the dimension goes above 2. So if I have, for instance, a three-dimensional integral current, can I say something more about the structure of the singularity? And if you remember what happened in the case of hypersurfaces, one first thing to bother about is whether your set is actually -2 rectifiable. And this is still open. And I will tell you more about this later. Okay, so now let me go actually to minimizing surfaces mod P, even in higher codimension. Okay, this is again possible. So for the modulus P equal to, Federer in 1970 actually proves that the singular set has dimension less or equal than m-2. And for P bigger than 2, in this work by Hirsch, Marchese, and Stuvard, and myself, we actually proved that the singular set has codimension 1 in the surface. If you remember, this was optimal even in the case of hypersurfaces. You cannot hope of doing better than that. So now, again, P equal 2 is done in the 1970s, way before Lagrange's theory, because it's still an epsilon regularity theory. So you don't have the problem of higher multiplicities, because P equal 2 means that your coefficient can only be 1 or 0. P bigger than 2 needs an Lagrange type theory, which actually has to be elaborated on purpose for solving this problem. Now, this also means that for P equal 2, Simon's techniques apply, and for P odd, even neighbor Valtorta. And you can say a little bit better, you can say the rectifiability, which is even though it seems like, you know, a sort of modest improvement, it's actually a big deal. But it's an open problem to prove the m-1 rectifiability for P bigger than 2 even. And I actually touched upon this in codimension 1. It's possible to do it in codimension 1 because we can prove actually much more. And I promised that I would tell you something about the case of codimension 1 and moduli P even, because I told you it's much more difficult than the case of P odd. So the reason for the difficulty is that if you go back to hypersurfaces, which are minimizing mod P, there is a beautiful example by White in his 1979 paper for P equal 4 that actually shows that for even P, there might be area minimizing hypercurrents which have flat singular points. So it's a case of codimension 1 in which we cannot deal with singularities only by having an epsilon regularity theory. We really need to actually develop an Lagrange type theorem. And that's why the proof was so complicated, and it was only done very recently. Okay, so now let me migrate to the boundary for the very final part of the talk. So if you are at the boundary, you remember in the case of hypersurfaces, you had the beautiful theorem by Hard and Simon, which tells you that there's not going to be any singularity. But in higher codimension, there are singularities. And it's very simple example is to take a half plane in a half, say, complex line in C2 and the full plane and chop it with a unit ball, say in R4. So now when you do that, your boundary is going to be a segment which goes through the origin and which is closed by half of a great circle on the sphere, plus a disjoint great circle. It's a very nice boundary, but nonetheless, the origin is a singular point, because at the origin, you have the crossing of this half plane and this full plane. But you can actually do much worse. So you can engineer a much nastier example around a branching, using a branching holomorphic curve. So here is the example. So you have to imagine now that, this arrow Z2 is a complex number, and the two in-plane lines are actually the real part of the other complex number and the imaginary part of the complex number. And what you're doing, you're following a branching surface around, a surface which branches 2 times. So you're actually following the branch up until here, and then here, instead of following the branch, you connect it to the branching point, and then you jump to the other branch and you connect it over here, and you form somehow a closed loop, which is nice, which by Federer's theorem is actually bounding a surface which branches at the singularity. Now, you can actually explicitly write down the parameterization for this curve gamma. And you see that it's not exactly C infinity, it's not smooth. You can actually do an example which is smooth, but it's at least this example over here, k time differentiable for any k that you might fix. It's a nasty example. It's again an example for which you have a flat singular point. So now recall Allard's boundary regularity theorem. So if your surface gamma is lying in the boundary of a smooth uniformly convex set omega, then there are no boundary singularities. And the reason is that if gamma is lying on some convex set, there's no way you can actually get this piece of the surface. You would actually lie all on one side. Okay, but you don't have this at disposal in general. And so here's an explanation of why under Allard's assumption you have full regularity. And without a convex barrier, you actually need an ungrained type theory at the boundary. And this was developed by Guido De Filippis, Jonas Hirsch, Annalisa Massacesi, and myself in 2018. And in there, we could actually prove that in general dimension and codimension, if you have an m-dimensional area minimizing integral current, which spans a single nice submanifold gamma, then the set of boundary regular points is open and dense. Or in other words, the set of singular points at the boundary is closed and meager. Now, when we actually had this theorem, we thought it was a lame theorem because we were expecting something much better. But in fact, it turns out it's essentially optimal. So in the same paper, we give an example of a one-dimensional curve in R4 and an area minimizing two-dimensional current whose boundary singularities form a Cantor-like set, which actually has full dimension 1. Now, you might a little bit object to this example in the sense that these singularities are somewhat mild. So in most of the points, you can actually decompose your surface into nice smooth pieces which are self-intersecting. So branching singularities are actually more rare. And in fact, we advanced the conjecture that for multiplicity 1 boundaries, boundary singular points, first of all, have 0 m-1 dimensional measures. So you can, in fact, improve upon the meagerness of the singular set. But also, the real singularities, so the singularities where you actually see branching, instead of having self-intersecting smooth pieces, must have codimension 2 in the surface or codimension 1 in the boundary. So for instance, for two-dimensional surfaces, just points. There's a beautiful conjecture by White also that actually says that if you take a real analytic curve gamma, then actually the boundary singularities in any sense that you have is going to be formed by isolated points. And that actually is really beautiful because he proves that if this conjecture were true, then your minimizer, your oriented minimizer, is a classical branched surface with finite topology. So you would be able actually to capture it even through the Douglas-Rado theory. But pay attention. So there is a theorem that we proved recently with Guido and Jonas, which shows how subtle actually this conjecture by White is. you can find a C-infinity closed Riemannian 4 manifold and a smooth, simple closed curve inside, which actually bounds an area minimizing two-dimensional current with an infinite number of boundary branching points, which of course are accumulating somewhere. But you can actually do even something nastier. So that the same idea, you can find again a closed smooth 4-dimensional manifold and a curve inside, which bounds a unique area minimizing oriented surface, which has infinite topology. So this means that if you actually take the Douglas-Rado approach and you minimize on some fixed topology, so say on some fixed surface of genus G, you're never going to actually capture the absolute minimizer for this particular surface gamma. You always get something which is a little bit worse. You get the best surface of genus G. Okay, so let me get towards the end of the talk. So concerning boundary regularity, there is a beautiful problem which is almost completely open, which is what actually happens if you have a boundary which is taken with multiplicity higher than 1. This was posed by Allard in 1969 in his PhD thesis, where he actually proved the first boundary regularity theorem for minimizers, and was raised again by White in his paper in a list of open problems in 1983. So it is false in this case that the minimizer is going to have necessarily the same multiplicity as the minimizer when you take a boundary with multiplicity equal 1. So think about having now again 2 planar circles, and they are in R3 and they have opposite orientation. So if you arrange the distance between these 2 circles correctly, actually gamma bounds 2 distinct area minimizing integral currents, T1 and T2. So one of them is the union of 2 oppositely oriented disks, but the other one is a single catenoidal surface joining them. So it's going to be the lateral surface of a cylinder which is slightly deformed. Now, if I give you 2 copies of this circle and 2 copies of this circle, the sum of these 2 minimizer is also area minimizing. So I can take as a minimizer the union of these 2 disks and the lateral surface. Of course, I can also take twice this disk and twice this disk, or twice the lateral surface. So you have 3 distinct minimizers. But now you notice that if you take this minimizer at the boundary, you don't see a single smooth surface which is coming at the boundary and picking up the multiplicity because it comes with the correct multiplicity. You see locally 2 different nice surfaces which are touching transversally at that point and which are both regular with multiplicity 1. And they both contribute to the multiplicity of the boundary reaching this 2. Now, in codimension 1, there's a general decomposition theorem which tells you that if you have a minimizer with higher multiplicity, you can always chop it into a bunch of minimizers with multiplicity 1. And then you can apply the Hart-Simon regularity theory for each minimizer, and you can use the boundary lemma to actually show that things are nice. But this decomposition theorem is false in higher dimensions. So, and this was proved actually by Elsie Young already in 1963. So in higher codimension, this problem is very, very hard. And there's just very little in the literature. So we just scratched the surface very recently. So there are just 2 results for 2-dimensional minimizers in any codimension. So first paper by Stefano Nardulli, Simone Steinbrüchel, and myself, which proves full regularity if you have a convex barrier. And then a second by Stefano and Reinaldo Resende de Oliveira, which actually proves that boundary regular set is dense in general for 2-dimensional minimizers. Okay, so in the very, very, very last minutes, I want to touch upon further directions which go beyond just understanding how large the singular set might be. So remember that I have this theorem by Almgren, which tells you this big regularity theorem, which tells you that if you have an m-dimensional area minimizing current in Rm plus n, then the singular set has dimension m-2 at most. And we know that if m is equal to, the singularities are isolated. We would actually like to show that if you are in higher dimension, then the singular set is at least m-2 rectifiable, almost a C1 submanifold. And this is widely open. Recall that the problem is that we have flat singular points And recall that Algrange's theory provides us this osculating smooth manifold and this Q-sheeted harmonic approximation. So in a couple of very recent works with Anna Skorobogatova, we are trying to deal with this difficulty that Algrange's theory is not so easy to modify, so to get actually rectifiability. So what we can actually prove is that this Q-sheeted approximation, which I told you, can actually be taken to be radially homogeneous. So it has a very nice structure. And this homogeneity has to be at least 1. And the point depends on the point Q when you're looking at, but not on the scale. So around the same point at smaller and smaller scales, this approximation actually has a certain radial behavior, which is fixed by the point and not by the scale. And this is what we call singularity degree of your current at that point. Now, if the singularity degree is bigger than 1, actually T is flat at all scales, and there is a unique approximating plane, even though the surface is not smooth. And if the degree is even bigger, this osculating manifold is actually the same through all scales. And by using these informations, we can modify the neighbor Valtorta theory, and this builds upon an intermediate work by Marchese, Spadaro, Valtorta, and myself. And we can prove that as long as the singularity degree is bigger than 1, actually you form an m-2 rectifiable set. So the big open problem is to understand the one which have actually degree 1 singularity. And what is the big challenge? Well, the big challenge is that, unfortunately, when the degree is equal to 1, we bump into one of the most formidable open questions in the area. That is that the approximating plane, which exists at certain scales, might actually depend on the scale. So there's some general thing that you can say, which is known since the dawn of the regularity theory. That is that at singular points, just out of simple compactness argument and a powerful monotonicity formula, homothetic rescalings of your minimizer or of your generalized minima surface have to converge up to subsequences to a generalized minimal cone. But there is this up to subsequences caveat. So a huge open problem, which is one of the most challenging in the area, is whether the limit of these rescalings depend or not on the subsequence. There are beautiful results by Taylor that we saw, by Allard and Lagrange, and above all, this beautiful work by Leon Simon in 1983, and then which in the case of isolated singularities, which have multiplicity 1 cones, actually shows uniqueness of the tangent cone. But what is especially difficult is actually to get uniqueness of tangent cones when the multiplicity is above 1. And for this, essentially, there's just one beautiful paper by White in 1982, which deals with 2-dimensional objects. Well, the last question that I want to raise is, can we actually go beyond rectifiability? So in a lot of situations, we have examples in which the singularities are actually C1 submanifolds. For instance, in the case of Taylor's theorem and the case of hypersurfaces mod P. You can actually wonder whether this is true in general. And there are 2 surprising, groundbreaking works which just appeared in the last couple of years. So one last year by Simon that actually shows that in codimension 1, stable minima surfaces might have singularities which are just arbitrary fractal, as long as you don't go above the dimension bound, which is given by the Schoen-Simon theory. And a more recent result in 2022 by Liu this year that actually shows that in codimension higher than 1, you can actually prove that there are minimizers which have fractal singular sets with any dimension which is below the bound of Algrange in his regularity theory. And the only drawback of these examples is that they are in some Riemannian manifold M, which are just smooth but not real analytic. So it seems that if you actually want to hope for better structure, you really should go with something which uses the real analytic assumption. And okay, so with this, I wish to thank you all for your attention, and this was the end of my talk.
So thank you, Camillo. So the timing was really perfect. Unfortunately, we don't have time for questions, but I think Camillo will be happy also to answer a few questions, not live, but later separately. So thank you again, and many thanks to all the attendees. Bye.